Hello, listeners. This is Mike, your host. If you are enjoying these archive episodes, please consider supporting the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Hopefully, with your support, I can continue to release these archive episodes. Thanks.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
I feel okay, I'm on.
How does it feel for the United States to be the new record holder?
At last, huh? When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Listen, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 144 of the Space Rocket History Podcast. And now, Lunar Orbiters 2 through 5 and Wresat. A total of 5 Lunar Orbiter missions were launched by the U.S. in 1966 through 1967. Lunar Orbiter 1 was covered in episode 75, so this episode will cover Lunar Orbiters 2 through 5. The purpose of the Lunar Orbiter series was to photograph the Moon's surface for selection and verification of safe landing sites for Surveyor and the Apollo missions. All lunar orbiters were equipped to collect selenoidetic data, which applies to mapping the Moon's size, shape, surface topology, and its gravitational and magnetic fields. They were also equipped to collect radiation intensity and micrometeoroid impact data. The orbiters had a mass of approximately 385 kilograms. All the orbiters were launched from Cape Canaveral using the Atlas SLV-3 and the Agena-D launch vehicle. The first 3 missions were dedicated to imaging 20 potential lunar landing sites selected by Earth-based observations. These missions were flown at low inclination orbits. The 4th and 5th missions were devoted to broader scientific objectives and were flown in high-altitude polar orbits. Lunar Orbiter 4 photographed the entire near side and 95% of the far side, and Lunar Orbiter 5 completed the far side coverage and acquired high and medium resolution images of 36 pre-selected areas. Now I want to describe the physical attributes of the Lunar Orbiter series. The main bus of the Lunar Orbiter series had the general shape of a truncated cone. It was 1.65 meters tall and 1.5 meters in diameter at the base. The spacecraft was comprised of 3 decks supported by trusses on an arch. The equipment deck at the base of the craft held the battery, transponder, flight programmer, inertial reference unit, Canopus star tracker, command decoder, multiplex encoder, amplifier, and the photographic system. 4 solar panels were mounted to extend out from the deck with a total span across of 3.7 meters. Also, extending out from the base of the spacecraft were a high-gain antenna on a 1.3 meter boom and a low-gain antenna on a 2.1 meter boom. Above the equipment deck, the middle deck held the velocity control engine, propellant, oxidizer, and pressurization tanks, sun sensors, and micrometeoroid detectors. The third deck consisted of a heat shield to protect the spacecraft from the firing of the velocity control engine. The nozzle of the engine protruded through the center of the shield. 4 attitude control thrusters were mounted on the perimeter of the top deck. 375 watts of power was provided by the 4 solar cell arrays, containing 10,856 solar cells, which would directly run the spacecraft and also charge the 12 amp-hour nickel-cadmium battery. The batteries were used during brief periods of occultation when no solar power was available. Propulsion for major maneuvers was provided by the gimbaled velocity control engine, a hypergolic 100-pound thrust Marquardt rocket motor. 3-axis stabilization and attitude control were provided by 4 1-pound nitrogen gas jets. Navigational data was provided by 5 sun sensors, Canopus star sensor, and the inertial reference unit equipped with internal gyros. Communications were via a 10-watt transmitter and the directional 1-meter-high gain antenna for transmission of photographs, and a 0.5-watt transmitter and omnidirectional low-gain antenna for other communications. Both antennas operated in the S-band at 2.295 GHz. Thermal control was maintained by a multi-layer aluminized mylar and Dacron thermal blanket which enshrouded the main bus. Several paint, insulation, and small heaters were used as well. Here's the NASA clip describing the Lunar Orbiter.
When astronauts stand on the surface of the moon, they will be part of what President Kennedy called the most hazardous and dangerous and greatest adventure on which man has ever embarked. But man hasn't arrived there yet. There is still a lot to be learned about this strange, hostile world. As far back as 1959, plans were being made for exploring the surface of the moon with unmanned spacecraft capable of photographing it, analyzing it, and measuring it. The third of these unmanned missions is Lunar Orbiter, in which an orbiting satellite takes pictures of the moon and transmits them back to Earth. Over 50,000 square miles of the visible moon's surface have been photographed with 100 times better resolution than has been possible with Earth-based telescopes. 6,000 square miles of it nearly 1,000 times better. Lunar Orbiter is best described as an orbiting photographic laboratory. Unlike earlier photo missions which used a television type of camera, Orbiter takes its pictures on 70mm film. It develops the pictures and stores them until it is time to send them back to Earth. The whole craft is similar to a 4-leaf clover with a thick stem. The leaves contain the solar cells that provide power for the various systems on board. And the stem contains the 2 lenses, the film processing unit, the picture transmission equipment, and the various scientific instruments, such as micrometeorite detectors and radiation counters. At the heart of Lunar Orbiter is the photo system. Pictures are taken simultaneously with the 2 lenses, one close-up and one wide angle. A device called a velocity height sensor determines the speed of the spacecraft relative to the moon's surface, normally over 4,000 miles an hour. As an exposure is being made, it moves the film proportionately to avoid blurring the image. The film then moves into the processor, where it is rolled into contact with a bimat web, a material that has been soaked in a solution that develops and fixes the image. It is then separated from the web and dried. The method of getting the picture from the moon to Earth is one of its most exacting tasks. The film is scanned by a light beam 1/20th as thick as a human hair. As the beam passes through the film, its intensity varies as the density of the image varies, and this variation is detected by a photoelectric cell. This converts the light into electronic signals which are transmitted to Earth. They are then converted back to light, and the picture is reconstructed. Each frame, consisting of one close-up and one wide-angle photo, requires 45 minutes of transmission. A typical Lunar Orbiter mission begins, after all of the checkout procedures have been completed, with the orbiter perched atop an Atlas Agena launch vehicle at Cape Kennedy, protected by a magnesium shroud. The Atlas ignites, pushing the spacecraft through the thicker atmosphere. After a little more than 5 minutes, the Atlas engines shut down, and the stage separates and falls away, followed in a few seconds by the shroud. The Agena second stage engine ignites long enough to place the combination into a parking orbit, a temporary one about 100 miles high, where the attached vehicles coast. When they arrive at an acceptable position from which to head for the moon, the Agena's engines ignite for the second time, boosting the spacecraft out of its parking orbit. The Agena then separates, sending the spacecraft on its way to the moon. Then, on command from Earth, the Lunar Orbiter begins to assume its familiar shape. The solar panels fold out to pick up the sunlight, and the radio antennas are extended for communications with Earth. A sensor locks onto the sun, aiming the panels so they can begin transforming the sun's energy into needed electricity. Several hours later, another sensor, designed to respond to Canopus, the brightest star in the southern sky, picks it out and locks on it. These two lock-ons are necessary so that ground controllers know the position of the spacecraft for future maneuvers. For the next several hours, the course of the spacecraft is carefully plotted against the known path of the moon. A decision can be made that a mid-course correction is required for perfect aiming. This is accomplished by rolling and pitching the spacecraft to the desired attitude and firing the velocity control engine a given period of time, either to speed it up or slow it down relative to the speed and direction of the moon itself. Orbiter 3, for example, was so accurately started on its way that it needed only a 500-mile adjustment in its initial aiming point. The orbiter arrives at the moon at a speed of about 4,500 miles per hour. If this speed is maintained, it will pass the moon and go on into an orbit of the sun. Once again, at the appropriate time, the spacecraft's attitude is adjusted and the engine is fired to slow it down to 2,200 miles per hour. It is attracted by the moon's gravity and swings into lunar orbit. For several days, the controllers study its orbit to determine precisely where it is. Then, for the third time, it is properly oriented and its velocity lowered to drop it down into its picture-taking orbit, ranging from 1,150 miles to about 28 miles. It is ready to start its photographic mission.
Now let's move on to the flights. First, we have Lunar Orbiter 2. Lunar Orbiter 2 was launched from Cape Canaveral Launch Complex 13 on November 6, 1966. After 92.5 hours flying time, Lunar Orbiter 2 was placed in a cislunar trajectory and injected into an elliptical near equatorial lunar orbit for data acquisition. The initial orbit was 196 kilometers by 1,850 kilometers at an inclination of 11.8 degrees. The Paraloon was lowered to 49.7 kilometers 5 days later after 33 orbits. On December 7th, a failure of the amplifier occurred, which resulted in the loss of 6 photographs. On December 8, 1966, the inclination was altered to 17.5 degrees to provide new data on lunar gravity. The spacecraft acquired photographic data from November 18th to the 25th, and readout occurred through December 7th, 1966. A total of 609 high-resolution and 208 medium-resolution frames were returned, most of excellent quality, with resolutions down to 1 meter. These included a spectacular oblique picture of the Copernicus crater, which was dubbed by the news media as one of the great pictures of the century. Accurate data were acquired from all other experiments throughout the mission. 3 micrometeorite impacts were recorded. The spacecraft was used for tracking purposes until it impacted the lunar surface on command on October 11, 1967. Now here's a clip for Lunar Orbiter 2.
But all the year's earthly events are eclipsed by America's achievements in space. Lunar Orbiter 2 heads for the moon to take pictures of future landing sites. This space photo lab shoots, develops, and transmits the film to Earth, where scientists examine it. First photographs show part of the Sea of Tranquility, a broad crater-pocked equatorial plain, landing field for U.S. astronauts in 1970.
Lunar Orbiter 3 launched from Cape Canaveral Launch Complex 13 on February 5, 1967. The spacecraft was placed in a cislunar trajectory and injected into an elliptical near equatorial lunar orbit on February 8th. The orbit was 210 kilometers by 1,802 kilometers, with an inclination of 20.9 degrees and a period of 3 hours 25 minutes. After 4 days of tracking, the orbit was changed to 55 kilometers by 1,847 kilometers. The spacecraft acquired photographic data from February 15th to the 23rd, and readout occurred through March 2nd, 1967. The film advance mechanism showed erratic behavior during this period, resulting in a decision to begin readout of the frames earlier than planned. The frames were read out successfully until March 4th, when the film advanced motor burned out, leaving about 25% of the frames on the take-up reel unable to be read. A total of 149 medium-resolution and 477 high-resolution frames were returned. The frames were of excellent quality, with resolution down to 1 meter. Included was a frame of the Surveyor 1 landing site, permitting identification of the location of the spacecraft on the surface. Accurate data were acquired from all other experiments throughout the mission. The spacecraft was used for tracking purposes until it impacted the lunar surface by command on October 9, 1967. Now, moving on to Lunar Orbiter 4. After the 3 previous orbiters had completed their required needs for Apollo mapping and site selection, Lunar Orbiter 4 was given a more general objective to perform a broad systematic photographic survey of lunar surface features in order to increase the scientific knowledge of their nature, origin, and processes, and to serve as a basis for selecting sites for more detailed scientific study by subsequent orbital and landing missions. Lunar Orbiter 4 was launched from Cape Canaveral on Launch Complex 13 on May 4, 1967. The spacecraft was placed in a cislunar trajectory and injected into an elliptical near-polar high lunar orbit for data acquisition. The orbit was 2,706 by 6,111 kilometers, with an inclination of 85.5 degrees and a period of 12 hours. After initial photography on May 11, 1967, problems started occurring with the camera's thermal door, which was not responding well to the commands to open and close. Fear that the door could become stuck in the closed position, covering the camera lens, led to a decision to leave the door open. This required extra altitude control maneuvers on each orbit to prevent light leakage into the camera, which would ruin the film. On May 13th, it was discovered that light leakage was damaging some of the film, and the door was tested and partially closed. Some fogging of the lens was then suspected due to condensation resulting from the lower temperatures. Changes in the altitude raised the temperature of the camera and generally eliminated the fogging. Continued problems with the readout drive mechanism, starting and stopping beginning on May 20th, resulted in a decision to terminate the photographic portion of the mission on May 26th. Despite problems with the readout drive, the entire film was read and transmitted. The spacecraft acquired photographic data from May 11th to the 26th, and readout occurred through June 1st, 1967. The orbit was then lowered to gather orbital data for the upcoming Lunar Orbiter 5 mission. A total of 419 high-resolution and 127 medium-resolution frames were acquired, covering 99% of the Moon's near side at resolutions from 58 to 134 meters. Accurate data was acquired for all other experiments throughout the mission. Radiation data showed increased dosages due to solar particle events producing low-energy protons. The spacecraft was used for tracking until it struck the lunar surface due to the natural decay of the orbit, no later than October 31st, 1967. And lastly, we have Lunar Orbiter 5. Lunar Orbiter 5 was launched from Cape Canaveral Launch Complex 13 on August 1st, 1967. Lunar Orbiter 5, the last of the Lunar Orbiter series, was designed to take additional Apollo and Surveyor landing site photography and to take broad survey images of unphotographed parts of the Moon's far side. The spacecraft was placed in a cislunar trajectory and on August 5, 1967 was injected into an elliptical near-polar lunar orbit of 195 kilometers by 6,023 kilometers with an inclination of 85 degrees and a period of 8 hours 30 minutes. On August 7th, the perilune was lowered to 100 kilometers, and on August 9th, the orbit was lowered to a 99 kilometer by 1,499 kilometers, with a 3-hour 11-minute period. The photographic portion of the mission ended on August 18th. The spacecraft acquired photographic data from August 6th to the 18th, 1967, and readout occurred until August 27, 1967. A total of 633 high-resolution and 211 medium-resolution frames at a resolution down to 2 meters were acquired, bringing the cumulative photographic coverage by the 5 lunar orbiters to 99% of the Moon's surface. Accurate data were acquired from all other experiments throughout the mission. The spacecraft was tracked until it impacted the lunar surface by command on January 31st, 1968. Now I want to talk a little bit about the photographs returned from the orbiters. The photographs were transmitted to Earth as analog data after onboard scanning of the original film into a series of strips. The data was written to magnetic tape and also to film. The film data was used to create handmade mosaics of lunar orbiter frames. Each lunar orbiter exposure resulted in 2 photographs, medium resolution frames recorded by the 80mm focal length lens and high resolution frames recorded by the 610mm focal length lens. Due to their larger size, high-resolution frames were divided into 3 sections or subframes. Large format prints from the mosaics were created and several copies were distributed across the U.S. to NASA image and data libraries known as Regional Planetary Information Facilities. The resulting outstanding views were of generally very high spatial resolution and covered a substantial portion of the lunar surface, but they suffered from a Venetian blind striping, missing or duplicate data, and frequent saturation effects that hampered their use. For many years, these images have been the basis of much of lunar scientific research. Because they were obtained at low to moderate sun angles, the lunar orbiter photographic mosaics are particularly useful for studying the morphology of lunar topographic features. In the year 2000, the Astrogeology Research Program of the U.S. Geological Survey in Flagstaff, Arizona, was funded by NASA as part of the Lunar Orbiter Digitization Project to scan at 25 micrometer resolution archival lunar orbiter positive film strips that were produced from the original data. The goal was to produce a global mosaic of the Moon using the best available lunar orbiter frames. The frames were constructed from scanned film strips. They were digitally constructed, geometrically controlled, and map projected without the stripes that had been noticeable in the original photographic frames. Because of its emphasis on construction of a global mosaic, this project only scanned about 15% of the available lunar orbiter photographic frames. Data from the lunar orbiter missions 3, 4, and 5 were included in the global mosaic. In addition, the U.S. Geological Service digitization project created frames from very high-resolution lunar orbiter images for several sites of scientific interest. These sites had been identified in the 1960s when the Apollo landing sites were being selected. Frames for sites such as the Apollo 12 landing site, the Marius Hills, and the Sulpicus Gallus Reel have been released. In 2007, the Lunar Orbiter Image Recovery Project began a process to convert the Lunar Orbiter images directly from the original analog video recordings of the spacecraft data to digital image format, a change which provided vastly improved resolution over the original image released in the 60s. The first of these restored images were released in late 2008. Almost all of the Lunar Orbiter images have been successfully recovered as of February 2014 and are undergoing digital processing before being submitted to NASA's Planetary Data System. In conclusion, the 5 lunar orbiters returned photography of 99% of the surface of the Moon, both near and far side, with resolution down to 1 meter. Altogether, the orbiters returned 2,180 high-resolution and 882 medium-resolution frames. The micrometeoroid experiments recorded 22 impacts, showing the average micrometeoroid flux near the Moon was about 2 orders of magnitude greater than in interplanetary space, but slightly less than the near-Earth environment. The radiation experiments confirmed that the design of Apollo hardware would protect the astronauts from average and greater than average short-term exposure to solar particle events. The use of lunar orbiters for tracking to evaluate the Manned Spaceflight Network tracking stations and Apollo Orbit Determination Program was successful with 3 lunar orbiters, 2, 3, and 5, being tracked simultaneously from August to October 1967. The lunar orbiters were all eventually commanded to crash on the Moon before their attitude control gas ran out, so they would not present navigational or communication hazards to later Apollo flights. The Lunar Orbiter program was managed by NASA's Langley Research Center at a total cost of $163 million. The final topic I want to cover today is Australia's first satellite. It was called Wresat, spelled W-R-E-S-A-T, which stands for Weapons Research Establishment Satellite. Using a spare American Redstone rocket from the tripartite Sparta project conducted at Woomera, Wresat was designed, developed, built, and successfully launched in just 11 months. Now, there is an interesting story of how all this happened. The United States had been utilizing the facilities of Woomera to conduct tripartite research with Australia and Great Britain into the physical effects of high-speed re-entry of warheads, an activity known as Project Sparta. Project Sparta utilized 3-stage launch vehicles, the first stage being the highly successful Redstone rocket, with the second and third stage being solid propellant-based. 9 Sparta launch vehicles and 1 spare were sent to Australia for use in the project. However, since no launch failures occurred, the spare Sparta launch vehicle was not going to be used. The options were either use it or return it to the United States, where it might possibly have ended up in a garbage dump. Instead, the Australians seized the opportunity and quickly developed proposals on what to do with the spare Sparta launch vehicle. Eventually, funding was secured, not necessarily because of the sound arguments presented to the Australian government on how useful the Wresat experience would be for upcoming trials, but quite likely because it was an inexpensive opportunity to gain some experience in space exploration for Australia. Design work on Australia's first satellite began in early 1967 as a joint venture between the Weapons Research Establishment and the University of Adelaide. The project aimed to improve the understanding of the effect of upper atmosphere on climate and weather and assist the U.S. in obtaining the physical data for research programs. The project also aimed to develop techniques for launching trials in the European Launcher Development Organization and British satellite programs, and demonstrate an Australian capability for developing a satellite using advanced technology and existing low-cost launch facilities at Woomera. Very early in the Wresat project, it was decided that for simplicity, Wresat would be integrated directly into the Sparta launch vehicle's third stage. In order to achieve an accurate orbital insertion, the combined second and third stage was spun to approximately 2 revolutions per second. The Wresat package was a little over 2 meters long and weighed approximately 72.5 kilograms. Wresat was battery-powered with no solar cells and thus would only operate for a short period of time in space. An interesting point to note about the Wresat design is that even though Wresat was spinning around its long axis at orbital insertion, this was not the preferred orientation for the scientific payload. The Wresat had an energy dissipator, which was a closed hydraulic loop of silicon oil, which dissipated the rotational energy as heat. The net result was the Wresat eventually tumbled around its short axis, which places the axis of rotation pointing out into space. Wresat carried scientific instruments which were very similar to those carried on sounding rockets already being used at Woomera. As such, these sensors were predominantly for upper atmospheric research. There were sensors to measure solar radiation, specifically 3 wavelengths which had the greatest impact on the temperature and composition of the upper atmosphere. The same sensors could also measure the temperature of the solar atmosphere and the density of molecular oxygen in the Earth's atmosphere. Additionally, there was a small telescope with a lithium fluoride lens which could measure the faint ultraviolet halo that surrounds the Earth at night. Now I have a partial clip of Wresat's final preparation and launch. The first part of the clip is cut off and I could not find the entire clip.
Sensors received a final check using a hydrogen light source rich in ultraviolet. The space between was flushed with nitrogen gas to prevent oxygen absorption. The radar transponder received a final check. Finally, the covers were fitted, the nose cone was screwed down, and Wresat was ready. It was then taken to the launching area for mating to the rocket. Here, with great care, to the relief of some and the confusion of the skeptics, it mated up perfectly, and the whole assembly was ready for launching. Erection was completed, the umbilical cord was attached. Through this cord, monitoring functions were maintained, and power was supplied to ignite the rocket engines. In the nearby control van, missile functions were checked. When all was well, the countdown began. The optical tracker had a hazy view of the launcher scene due to the high ground temperature. As the countdown proceeds, the heater-cooler drop tank is shed. Light up. Lift off.
Wresat was launched on November 29, 1967, atop the spare Sparta launch vehicle from Woomera's Launch Area 8, the same pad as used for the 9 Project Sparta launches. The launch track was polar, slightly east of due north, the same as the European Launch Development Organization's F-4. The launch was successful, with Wresat entering an elliptical polar orbit and becoming operational. The perigee was 198 kilometers and the apogee was 1,252 kilometers, with an inclination of 83.3 degrees and an orbital period of 99.3 minutes. However, with only batteries to provide power, Wresat operated for only 2 weeks. The low perigee of the orbit, 198 kilometers, also meant that the orbit would degrade rapidly. Wresat completed 642 orbits and transmitted scientific information for 73 orbits to tracking and research stations around the world. It re-entered the Earth's atmosphere and was destroyed by the resultant high temperature on January 10, 1968, over the Atlantic Ocean west of Ireland. Thus, the first Australian satellite lasted 43 days in orbit. Apart from the experimental data obtained, Wresat contributed both to the knowledge of the solar-terrestrial relationship and to the studies of atmospheric composition. The project also presented an opportunity for a united approach to a scientific problem with demanding requirements. Such was the interest in space technology that the Wresat prototype was exhibited in Parliament House, Canberra, and at the London Trade Fair in 1968. As an historical postscript, Woomera Township volunteers recovered the first stage of the Wresat launcher from the Simpson Desert in April of 1990. The battered but surprisingly intact vehicle is now on display in the Rocket Park opposite the Woomera Heritage Center. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange donate button or the Patreon link. Thanks.